My name is Bruno. Previously in this track, we motivated the need for uncertainty measures. These were really crucial to inform the decisions that we take based on the output of a machine learning model. They are also really useful in determining what data to label next or where to collect more data from. Andre, in his video, introduced various measures of uncertainty and showed how this can be computed from the output of an ensemble of neural networks. Ensembles had one crucial drawback, however. They require storing and running multiple numbers of models at inference time. This means 5 times, 10 times, or more the computational cost, and translates to longer inference times or the need for more powerful hardware. In this video, I will address this limitation and introduce a simple engineering approach to getting around it. Firstly, let's quickly recap why ensembles are pretty great. Ensembles provide one particularly simple approach for getting measures of uncertainty. Just train several models, starting from different random initializations, and then use a set of predictions from the ensemble to get uncertainty estimates. Ensembles provide an easy way to get fairly robust measures of uncertainty, and also allow for distinguishing between knowledge and data uncertainty. This simplicity is in practice one of the method's greatest assets. Many competing methods derive from fundamentally elegant Bayesian approaches, but sometimes reading the paper and trying to understand all of the approximations made can feel daunting. Neural network ensemble approaches also work very well in practice. They have been shown to perform really well empirically on a wide variety of uncertainty-oriented tasks. On top of that, they also give a significant predictive performance boost of a single model. This last point alone is the reason why ensemble approaches end up being used in a large proportion of winning Kaggle competition submissions. However, as I mentioned, there is one key drawback. At inference time, when we make a prediction, each of the ensemble members has to be evaluated on the input. This translates to a big computational penalty when using an ensemble rather than a single model at inference time. This is a huge issue when deploying these algorithms in practice. Everyone is a huge fan of uncertainty-aware machine learning systems until they have to 10x the computational budget, fill up the weight of an autonomous vehicle with onboard GPUs, or make the user wait around for ages for a result.
Let's briefly talk about why ensembles allowed us to differentiate between different types of uncertainty. In a classification context, a single neural network usually outputs a categorical distribution, conditioned on the input. This is the output of the softmax layer. It assigns probabilities to each class label. This output can be visualized as a point on probability simplex. The probability simplex is simply the set of points in space, the coordinates of which describe a valid probability distribution. In other words, the coordinates have to sum to 1, and each coordinate has to be non-negative. Consequently, we can visualize any categorical probability distribution, or equivalently, the softmax layer of a neural network, as a point in space that lies on the simplex. In the 3-dimensional case, i.e. for probability distribution over 3 classes, this set of points looks like a triangle. The simplex gets harder to visualize for high dimensions, so we'll just stick with 3 for now. To summarize, the softmax layer of the neural network outputs a probability distribution over class labels that we can visualize as a single point on the simplex. An ensemble of those networks outputs a collection of points on the simplex. These softmax outputs from an ensemble of models can be seen as coming from a distribution over the simplex. Each time we evaluate a new member of the ensemble, we are drawing a new sample from the probability distribution over the simplex. Thanks to having multiple samples for a predictive distribution, we can assess the level of disagreement of different members of the ensemble. These, in turn, reflect the knowledge uncertainty in the prediction. So now, let's consider how a single neural network could emulate an ensemble of models. This network would have to output not just a single categorical distribution, but a whole distribution over possible categorical distributions that could be drawn from the ensemble. Hence, if we can parameterize a distribution over a simplex, we can emulate a whole ensemble with a single model. In other words, we would parameterize a high-order conditional distribution with that single model. One possible choice for a distribution over categorical distributions is a Dirichlet distribution. It looks somewhat like this. For a categorical distribution with k categories, the shape of a Dirichlet distribution is defined by k parameters alpha. So, if we let the outputs of a neural network specify these parameters, alpha, we've got a neural network parameterizing a Dirichlet distribution. There's just one quirk, namely, the parameters of a Dirichlet have to be greater than 0. Hence, we can pass the output of a neural network for an exponential function to make sure all of the outputs are positive. As a quick recap, we can use a neural network to parameterize a Dirichlet distribution, samples from which are categorical distributions and can be interpreted as predictions from individual members of an ensemble. Samples from these categorical distributions are then just classes. A neural network parameterizing a Dirichlet distribution in this context has been referred to as a prior network. With this network, we can emulate an ensemble of categorical distributions and distinguish between different types of uncertainty. We can compute a measure of spread, or diversity of the output Dirichlet, by computing the mutual information. We can compute the mutual information with this analytical formula, which roughly translates the following line of code in Python. Similarly, we can compute data uncertainty with this formula. The total uncertainty is then just the sum of the two. Note that we can compute these uncertainty measures with an analytical formula from a single pass from the neural network. We only have to evaluate one network once.
So far, we described how to parameterize the Dirichlet distribution of a neural network to emulate an ensemble. Consequently, we are able to compute ensemble-like measures of uncertainty from a single neural network model. However, one question remains as to how to train such a prior network model. One approach would be to take inspiration from ensemble distillation and distill the distribution of the ensemble into a single prior network model.
In standard ensemble distillation, the goal is to distill an ensemble of models into a single regular neural network in order to capture the predictive performance benefits. This is usually done by averaging the ensemble predictions and then training a regular neural network to match the mean of the ensemble. In short, ensembles give better performance than a single neural network, so let's train the neural network on the mean of the ensemble predictions to get better performance. If a performance boost is all we're after, this works well. However, by averaging all the ensemble predictions, information about the diversity of the samples from the ensemble is lost. Consequently, the information about the ensemble's knowledge and data uncertainty is also lost, and we are no longer able to compute measures of those. By distilling into a regular neural network, we lose the uncertainty estimation benefits that the ensemble provided in the first place. If we, on the other hand, distill the ensemble predictions into a prior network, we can retain the information about both the mean and the diversity of the ensemble. Recall that the prior network parameterizes a distribution over categorical distributions. Hence, it can distill information not only about the mean of the ensemble predictions, but also about how they are distributed on the simplex. Consequently, a prior network can learn how the diversity of the ensemble predictions changes depending on its input. Distilling an ensemble into a prior network is quite simple. Loosely speaking, we can distill the ensemble by trying to make the output of the prior network match the distribution of the predictions from the ensemble as closely as possible. The procedure consists of a few simple steps. Firstly, specify a transfer dataset. This can contain any data. It can consist of inputs from the original training dataset, or it can have some extra unlabeled data as well. Secondly, obtain predictions from the ensemble on the transfer dataset. These will be the labels for the network being distilled into. Given this dataset, then train the prior network by minimizing the negative log likelihood. In other words, we optimize the parameters of the prior network to maximize the probability of the ensemble predictions being drawn from the Dirichlet. For a Dirichlet distribution, the formula for the log likelihood looks like this, and it will be implemented somewhat like this. This is really all you fundamentally need to know to distill an ensemble into a prior network. However, there are some tips that can make the distillation procedure work much better. Firstly, to aid optimization, it helps to incorporate a temperature parameter. We can simply divide both the pre-softmax outputs of the ensemble and the pre-exponent outputs of the prior network by the same temperature parameter T. It helps to start training with a high temperature parameter and then gradually reduce it back to 1 during training. Another implementation detail worth discussing is how do you choose the transfer dataset. Using just the original training dataset as the transfer set is unlikely to yield the best results possible. This is because on the original training dataset, the ensemble predictions will be confident on almost all inputs. As a result, the model being distilled into would have seen very few examples of how the ensemble behaves in uncertain regions. Hence, it is very useful to include some auxiliary or augmented data on which the ensemble is likely to be uncertain. Note that this data doesn't have to be manually labeled, as labels for the transfer dataset come entirely from the ensemble.
Overall, this approach is great if access to compute at training time is not a major issue, but deployment time, inference has to be very efficient. This is a very common scenario. For instance, consider again machine learning algorithms for autonomous vehicles. At training time, models can be trained on dedicated workstations with many GPUs. But at inference time, they have to run on dedicated low-power hardware on a car, and predictions have to be made in real time. So to summarize, ensembles are a great practical method for obtaining uncertainty estimates. Unfortunately, they're computationally expensive. In this video, I showed you how an ensemble can be emulated with a single neural network by parameterizing a Dirichlet distribution. I also showed you how this network can be trained using ensemble distribution distillation by making the model mimic uncertainty estimates from the ensemble yet remaining computationally tractable at test time. The methods described in this video are specific to the classification task. However, the principles underlying these methods are fairly general. They can be applied to regression, sequence prediction, and many other tasks. In fact, in the next video, Ivan will introduce prior networks for regression and a similar ensemble distribution distillation training routine. For now, thank you for watching this video. I hope you enjoyed it.